Hello and welcome. My name is Michael Lee and I am one of the authors for the JME 410 Senior Design Project Materials Lab in a Briefcase. Basically today I'm going to be talking about the Senior Design Project for summer 2020. This project entailed the Materials Lab in a Briefcase, which for those that don't know is basically the unprecedented times of coronavirus and COVID-19. And the materials lab in a briefcase is something that can be used in an online environment to students around the world. So basically the materials lab in a briefcase is something that is able to be compacted down in the most simple form, and it can be shipped to people that are taking online classes away from campus and don't have access to a materials laboratory. Basically this kit or briefcase is essential for the material science courses that are being taught at various universities around the country and world. So for the first part of the experiment, we started with the idea of some conceptual drawings. Initial conceptual drawings were limited to what we knew from mechanical engineering and how we could get the most torque and most amount of forces out of a given specimen. However, during this 410 course, we found that the weight and size of components was going to be a main factor, because ultimately this materials lab in a briefcase had to be shrinking down to the size where it could be in a case that was put underneath a laboratory table. So initially we thought of using a piston cylinder with a press, and so as you can see from the very first drawing on the top left, the piston cylinder would push up. We would have a pressure gauge that would indicate how much pressure is in the sample, and ultimately at failure we would be able to see the amount of failure pressure in the gauge. This was a cool idea, except for the fact that it did not incorporate a sensor that could be sent to a computer, which is ultimately what the materials science courses teach. They teach a software aspect to materials science using tensile testers, hardness testers, Sharpie tests, and various other tests as well. And basically we eliminated this conceptual drawing because it didn't incorporate everything that had to be incorporated into our materials lab. And the fact that the weight was definitely a giant factor. We had a steel gusset and base plates, and we had steel presses. This was just too bulky of an item that we could throw into a case and send to somebody. So the alternative to our design was coming up with an Arduino electromechanical system that could drive some stepper motors to incorporate a force transducer. So this force transducer is universal load cell basically, and as the universal load cell goes up and down, the system exerts a force, and that force is then sent to a computer device through the Arduino. So the Arduino Uno, in our case, receives the information such as the amount of force, and then using other things such as like a strain gauge or anything like that, we're able to then get the stress strain curves because we know the dimensions of the material. So we're able to get the stress strain curves, and those can be sent to the graphs. So from these graphs, we're then able to get the true engineering strain and stress values that were most commonly seen in the materials lab courses that we're used to. So this kind of compact design is cool in the fact that we get a universal load cell that can be used in compression and tension. So for those that don't understand how that works or why that's significant, basically we're able to put two materials testing equipment into one. So the materials lab testing things that we're considering is the hardness tester and the tensile tester. The tensile tester operates in tension, while the hardness tester, known as the Brunel's hardness testing, is used in compression. So basically the stepper motors would drive down and create compression, and that would be useful for the HRB tests. So moving on to the next slide, we've decided that this is the kind of system that we were wanting to go with, something that could be plugged into a wall and used by students anywhere. So here's just some of the numbers that we came up with in our metrics table for the winning concept scores. Now keep in mind, when it came to the hardness tester, this was not the most ideal project. We actually had another hardness tester that was a handheld one, and it was much more efficient, except the only problem with that was we would have had to incorporate 2 components instead of just having 1. And the other tensile tester didn't make any sense to just keep the non-electromechanical system. It's because we just have one electric system and one mechanical system. So in order to eliminate this, we decided that the best metrics table was definitely incorporating the Arduino tensile tester and hardness tester into one. And right here you can see the total happiness values from our equations set up, and we have pretty similar happiness with both designs. So now getting into the embodiment and assembly and drawings for everything. Basically, this initial drawing is just the actual final drawing. So this is the final drawing that we came up with whenever we were designing this. We wanted something that we could put into a materials briefcase. We could put various other components such as solid solution hardening. So we left a little bit of room for aluminum samples. Basically, the aluminum samples would be thrown into the briefcase and gently formed in there. And when the students were able to use those at their own home, they would then take those samples, throw them into an oven, and basically bake them in a furnace. And what this would do is it would provide solid solution hardening. And obviously we would provide other materials such as a quench and other things as well to prevent any injury or anything like that from happening. So right here you can see the prototype in action from all angles, and some of the dimensions of the threaded rod, spacing, the length of the entire design, and how big of a table space that you would need for the case. So now moving on to some more detailed drawings that are ballooned out. You can see some of the parts that were shown. Figure balloon 8 in the top left corner. The balloon's basically showing the tensile tester cross member pieces, and balloon 13 shows the actual universal load cell. So basically this universal load cell would then send information to the Arduino, which would be balloon number 11. So we would run cables from 13 all the way down to the Arduino at number 11. Other things that we considered were the couplings. So when we were doing initial finite element analysis, we determined that emphasis on points such as the couplings, also shown as balloon number 4, and the threaded rods were key elements of analysis. So just keeping that in mind, we used basically what we show here in a different analysis as well later on in this presentation. So as I was saying, we used a different type of analysis. In this, we used a dynamic simulation. So Autodesk Inventor products allows for the dynamic motion of a component. Basically, you're able to apply forces and torques that are known in a very simple model that can then be transferred into finite element analysis. And so once you export these motions, it then turns everything into torques and moments on each part that's being acted on. So any load-bearing part will receive a finite element analysis while this is in dynamic simulation mode. So showing you this video, basically we applied a center load right here, and this center load was in tension and in compression. As you can see from the video, we moved it up, and then we moved it down. So in this specific video, we were applying 500 pounds force, and we were also applying the max NEMA motor torque that was specified on the manufacturer's website. So both motors are applying a torque, and also we're applying a force axially right down the middle. So what does this tell us? Basically what this tells us is the next part of the experiment, which is the dynamic simulation finite element analysis. Also, this is known as FEA. So from the FEA results, we were able to determine some of our maximum stresses. As you can see, we don't really go into the red at all. Our part is basically in the blue, which when considering things like von Mises stresses is very, very good. Highest stress would be anywhere between 56 to 84 KSI in our parts. And ultimately, because of the threaded rods that are made out of alloy steel, we're able to get values that are within the yielding range. So this wasn't of concern to us when we were running our FEA. Moving on to the next part, we did another one of the threaded rod, and again, what we seen was some very low von Mises stresses. So this was quite a new step in simulating software that we're able to take, where we don't necessarily need a working prototype anymore to determine what kind of loads that we're able to see in the part. And this reduces costs by a lot. Not having to build an actual prototype, so to speak, can show a lot in costs. Here's another view of the coupling that was receiving multiple moments and torques and forces being applied to it from the dynamic simulation. So this dynamic simulation basically said that we were going to have a really high stress at 165 KSI. And basically this finite element analysis told us that our part was basically going to fail, if anything, at this joint right here, which there's a lot of pressure going on at that joint. We have some moments being applied here, but we also have forces being applied at the bottom as well, because this is a keyway for the NEMA motor. So this keyway is getting contact as well and staying stationary. So we're applying two forces that are pulling this in and rotating it at the same time. And this was our conclusion upon this prototyping, is that we need to improve these joints as best as we can, because we were receiving a lot of stress, and if not improve the joint, we needed to improve the material. So we would have to switch to something like a titanium or anything like that, which would be costly but effective. So moving on to the next slide, we came to our final prototype and what we wanted to do. These are just some renderings that we took of the virtual laboratory kit. Basically, we show the front that you can see here. So this is the front view, and this is kind of a ortho view of the part. And then below, we see the left view. Moving on, this is kind of the assembly without the actual case in view. And from here, you can see kind of the clamping system that we have in place. We have these clamps up here, and then we have a clamp down here. The same clamp, there's in different locations. basically this is a threaded piece, and what we're able to do is we're able to take this piece out, we're able to take this piece out, and we could put in a Bernal hardness tester, and we can use this machine in the compression as well as tension. This piece is pretty essential to our project because it's able to reduce the amount of costs on material. We don't have to have two machines. We can just have one in one system, which was what we wanted to do. We wanted to reduce the weight and reduce the shape of the device. These are just some close-up pictures of key components. Right here we have the load cell, and we also have the clamping system. Below we have the clamp for the bottom, cross member, and this is the coupling again, some threaded rod that we have applying, and we also have the Niemer motor as well. We also have the framing and some of the framing connectors off to the left, and this is a micro stepper controller. So basically this runs to the Arduino motor, and we're able to run a micro step controller. That's the end of this presentation. I would just like to thank Mark Tequila and Craig Giesman for a challenging yet successful semester. We had the coronavirus going on, COVID-19. A lot of issues arose with manufacturing and prototyping, and without these guys, we wouldn't be able to do some of the things that we were able to do. So thank you guys for listening, and I hope you guys enjoyed.